Okay, hello everyone, and welcome to our Automotive EMI webinar. We're going to start in just a few minutes. I see some folks are still joining us. Before that, though, let me just say a couple of announcements. Today's session is our third automotive focus webinar in our ongoing series that we launched earlier this year. For those of you who joined us in the summer, we inaugurated the series with Fundamentals of EMI. And this really explored some of the foundational topics around EMC. So what exactly is EMC? We talked about the sources in a power supply design and, of course, provided general guidance on how to manage and how to reduce it. Our second webinar, which was last month in November, this covered the topic of AEC Q100 qualification. Of course, we found that a lot of our customers working on automotive systems demand AEC Q100 grade products, but a lot of folks may not really know exactly what this entailed. So this webinar provided a really nice background on automotive qualification. We talked about the different types of reliability testing that goes into certifying an automotive product. And we also talked about the different grades of solutions that MPS offers, from consumer to industrial and then to full automotive. Stay tuned, as next year we're going to continue this webinar series with even more episodes. We'll, of course, explore even deeper into the hot topic of EMI, and we'll also have focus sessions on other automotive power management topics. And you are all welcome to submit your topic ideas. You can reach us at automotive@monolithicpower.com. Today's webinar, if you have any questions, please use the Zoom app, and you'll find a Q&A option inside of the Zoom app. Please submit all of your questions through there, and Jens will respond to these at the very end of the presentation. We will make this presentation available for offline viewing. Expect an email to come through in the next day or two, and we'll also make the presentation available in a PDF format. All of the webinars that we've hosted this year are also available. The URL is monolithicpower.com/webinars. Again, that's monolithicpower.com/webinars. And of course, we'll include a link to this in the email that will be sent out later today or tomorrow. So now, without further ado, I'd like to turn it over to Jens Hedrick, our EMC expert based out of Germany.
Hello, I'm Jens Hedrich. I'm working since 2010 as FIE for Monolithic Power Systems. In Europe, I concentrate on industrial and automotive customers. During the last couple of years, I had a special focus on improving the EMC performance of our evaluation boards. So I worked a lot on the layouts with the team, and also spent a lot of time in automotive EMC labs to make tests and find out what helps to improve the EMC performance. I also supported customers troubleshooting EMC, and now we have a good series of high performance evaluation boards. Before MPS, I was 11.5 years FIE at Linear Technology. There I supported one of their EMC clean evaluation boards, the DC1212. And before becoming an FIE, I was hardware design engineer in Nokia mobile phones. During that time, I worked on an early automotive telematics system with eCall and emergency battery. So the agenda for today, I have some motivation slides. We walk through initial PCB real estate planning. We will have a look on how to utilize the layers of our multi-layer board for best performance. We will discuss copper under the inductor, yes or no. We will have a detailed look on a schematic and layout of one of our EMC optimized PCBs. I also have some EMC test results on this. We have a list of frequently asked questions that are answered at the end, and I try to answer the incoming questions at the end of this session. This is a evaluation board example that is optimized for thermal, but not for EMC. It doesn't have any input filter. It doesn't have a ground plane. It is only 2-layer. And it has, for example, a huge switch area on top and bottom side that is acting like a big patch antenna. If we test this board conducted emission according CISPA 25, we see a disaster. This is an example of a much better board that has an input EMC filter on the bottom side of the board, and it has a nice layout with 4 layers and a nice ground plane. This board fulfills CISPA 25 level 5 with margin, but it is sometimes a little bit tight for the tough automotive OEM limits. So we have an even better board. You can see here, for example, the conducted emission test result in the upper frequency range, and in the FM band, the automotive OEMs have 12 dB microvolt average limit, which is equal to 4 microvolt of noise voltage, or 80 nanoamps flowing in the 50 ohm input impedance of the EMC receiver. So almost nothing. How to get to this level? A quick reminder from the last webinar that Christian was holding. If we have the buck converter input stage with the 2 MOSFETs and the input capacitor placed on top of a copper plane, a ground plane, for example, we will see that the highest current density due to skin effect and proximity effect will be in the center of this loop. But also in the conductor at the outer edges, we see still a relative high current density. This high DIDT loop, of course, creates or has an AC magnetic field, which will induce eddy currents in the copper plane. These eddy currents have the opposite direction to the conductor above of them. In this very center, you will see 0 current density because we are between the 2 directions. But also we see at the edges of this copper conductor still significant current density, especially at the very edges. The distance of this loop above the ground plane with the eddy currents that try to mirror image the original hot loop current is very important. The closer together, the better. And if we increase the distance, we will also see that this eddy current area will spread wider and wider. If you want to have a real good EMC performance, we have to consider certain topics right from the beginning of the project. For example, if the DC-DC converter is placed too close to the connectors and cables, we will have the magnetic and electric field coupling directly into the connector and cable, and the cable will act as an antenna, and we have a radiation problem. Also, the EMC filter components, if placed too close to the converter, will pick up noise, and we will not get the needed attenuation from our filter to pass the EMC limits. So we have an EMC problem. What to do? Where to place the DC-DC? If you recall, in closed field condition, the field falls with 1 over distance in square. So what we can do is move the DC-DC converter away from any cable and connector. At least 3 to 5 centimeter distance, or 2 inches, is a good number to bring the field strength to a level that is acceptable and that we have a chance to pass the EMC limits. Ideally, we place the DC-DC converter on the opposite side of this PCB with respect to the connector, under a solid copper area. The EMC filter components should be placed close to the connector. Here's a side view of a single-side assembled PCB. We have the hot loop, input capacitor, and the DC-DC converter IC with the magnetic fields. And you can see below this solid copper plane, there's no AC magnetic field anymore. But you also see on this board there is no quiet place to effectively position our filter components and our connector and the cable termination. One thing we can do is, in such a board, is place a shield. If we place a shield, we get a picture a little bit like this. And a heatsink, for example, can act as a shield. How to use a multi-layer PCB to our advantage? You see here in this example, the top side copper routings of our circuitry. We have the V-in area, we have the power ground, we have the switch node, and here you would have the inductor connecting to the output side and the output ground area. We have the simplified high DIDT current loop. Actually, it would run on the edges of the copper areas. And what we do is we separate these power ground of the input stage from the other ground areas, and especially from the connector ground. And the only connection we establish is through vias and the inner layers that are used in a certain way to block the noise from this area with respect to the rest of the board. Every through via is around 1 nanohenry of inductance, and we try to use this to our benefit. In the layer under the DC-DC block, we should have a solid ground area that allows a good mirror image of the high DIDT current on the top side, and this way cancel magnetic field radiation on the top side. This ground is still noisy because the impedance of this layer is not zero, and the high DIDT eddy currents will create noise voltage. So this is purely the DC-DC reference ground and not the system reference ground, and definitely not the same ground reference for our connector. This would be EMC-wise not good. So the layer 3 and 4 are clean, and noise stays in the top 2 layers. The goal is that the ground area around the connector is very clean. Let's have a more three-dimensional look at the same thing. So we have the high DIDT loop on the top side. We have the separation cuts. So no direct ground connection on the top side, only through the vias. We have the eddy currents mirror imaging the top side high DIDT current loops. And the current density of these eddy currents is highest directly under the loop. But we remember at the edges, it's still greater than 0. And these eddy currents, of course, have also a magnetic field, and they can couple into other signals and connectors. The 2 bottom layers are clean. And if we look at the way our noisy DC-DC area is separated, we have several vias in between our critical cable connection and our EMC filter component places, either here or on the bottom side, and our noisy area. One question that is often discussed is place copper directly under the inductor. One opinion is the AC magnetic field in the center under the inductor core will create high eddy currents in the copper, and with this losses, and also these eddy currents will reduce the inductance value. Another opinion is, yes, place copper directly on the top side of the PCB to avoid that the AC magnetic field from the inductor is disturbing the layers of the PCB. What is right? Let's have a look. In this sketch, you see a bobbin type semi-shielded SMD inductor placed on a 4-layer board where no copper is placed under the core in all 4 layers. You also see that the start of winding is connected to the switch node, which gives a little bit lower E-field radiation from the inductor, as the outer winding which is connected to the output to a steady potential, will shield the E-field radiation. The magnetic field lines are sketched like this, and we see that the very strong magnetic field lines under the core of the inductor can close around the PCB And this way, they will fully couple into the cable and connectors and EMC filter components. We also see that this in yellow shown eddy currents at the edges of each hole in the layers is very high. We have eddy currents on top copper, which is good because the eddy currents have a magnetic field with the opposite direction to the original field. And at the copper, they will tend to cancel. This board has no quiet position to place EMC filter or a cable connection without EMC trouble. So very bad. Let's have a closer look on a copper area with a cutout in the center that is exposed to AC magnetic field from the hot loop or from the coil. So we see the field lines in the center go straight through, of course. We have eddy currents that are being induced. We have very high current density at the edges of the cut in the center of the board. But we also have a significant current density at the edges of the copper area. The eddy currents have magnetic fields also at the edges. And again, these eddy currents at the edges are also critical to couple into other areas. If we look on this example, where we have solid copper under the inductor in the layer 4, so bottom layer of the PCB, we see that the magnetic field lines, the AC magnetic field lines under this copper are gone because of the eddy currents that are induced in this copper. They have a magnetic field with the opposite direction. So below this copper, we don't have AC magnetic field anymore. We have high current density at the edges of the holes, and we have, of course, AC eddy currents flowing in the top copper. Here we don't have direct coupling from the magnetic field lines into the cable and filter components, or at least significantly reduced coupling. But we still have a problem. In this layer 4, which has an impedance greater than 0, we have high DIDT, eddy currents flowing, and they will create noise, which is a bad reference for our EMC filter components and especially for our cable connection. So there is not a really clean, noise-free place for our connections. So this board is much better, but still not optimum, as its reference is noisy. A much better way is to place copper really under all layers under the inductor, and especially directly on the top side, as the eddy currents that are building up in this top side copper will immediately block the high magnetic field strength from the inductor to enter the other layers of the board. The disadvantage is we have higher losses here in the copper, and we have a reduced inductance value. It's typically a number of a % or so. So this board offers a very clean bottom side ground reference for EMC filter and the cable connection. Another thing, if we place a solid copper ground plane directly under our component side, we will form a parasitic capacitor from the switch node of our converter that is connecting to the inductor. And we will have a parasitic current flowing during switch transition to ground. If you look at the routing of the 4430 3.5 amp synchronous buck converter layout, we see that the switch node is roughly 17 square millimeter in size. And with this 100 micrometer distance between the layers, between top and inner layer 1, we have around 100 picofarad of parasitic capacitance. If we compare this capacitance to the output capacitance of the bottom power MOSFET, we see this is a factor of at least 30 lower. The benefit of having a solid copper under the switch node, under the high DIDT area of our DC-DC converter, that allows eddy current to mirror image the high DIDT loops on the top side, and this way cancel the magnetic field radiation on the top side is more important than the additional parasitic capacitance with a factor of 30 lower. Let's have a look on the schematic of our EMC optimized demo board. We use a two-stage input filter with a small 1 microhenry or 805 inductor that can handle 3 amps and small 0805 1 microfarad capacitors. This filter stage gives at 450 kilohertz switching frequency around 19 dB attenuation. The second filter stage we built with a 4.7 microhenry inductor and two 1210 size 4.7 microfarad capacitors. This stage adds another 45 dB attenuation at fundamental frequency. So in total, we see 64 dB attenuation. This is pretty much, and actually today we changed the schematic a little bit, so we use more like 2 microhenry, sorry, on this position. And with this, we still get a total of 57 dB attenuation, which is usually sufficient. In this calculation, I assumed that the MLCCs have around 50% of the nominal capacitance when DC, 13 volt DC from the car battery is present. Here's a picture of the two-stage filter components compared to the classic single-stage input filter with a 10 microhenry inductor and two 10 microfarad 1210 size capacitors. Both filter structures have the same attenuation at fundamental frequency, but the two-stage filter has a much better attenuation at higher frequencies than the single-stage filter. You also notice in the schematic of our 4430 family evaluation boards, we have a pin-to-pin family, 1 amp to 3.5 amp. We have a 20 ohm series resistor with a bootstrap capacitor. And this capacitor, this resistor slows down the rising edge and reduces ringing and overshoot at the switch node. And it also reduces a high frequency energy from the switch voltage applied to the inductor, which is radiating E fields. So this resistor actually reduces a high frequency E field radiation of the coil. The other thing you see at this circuit is that we split the frequency determining resistor into two parts. And here in this point, we can induce a signal for spread spectrum frequency modulation. The top side copper of our board, you see the input voltage being routed here to the middle pin of the chip. You see the power ground U-shape area with the input capacitors. We have two sets of input capacitors that are placed symmetrically. So the IDT current will split up into two loops with opposite direction. You also see that we use two output capacitors next to this tiny inductor. The inductor is so tiny because this is a 4431, the 1 amp family member, and we can use a smaller component. But these capacitors block part of the E field radiation of the coil. You also notice that we have a ground cut at the capacitor return and the power ground. So there's no direct connection from the power ground to the surrounding ground areas on the top side, only through vias, and the vias block the high frequency from entering the PCB and disturbing other layers. The surrounding ground of this block is a DC-DC ground, which is also the output capacitor ground reference and is also the analog ground reference of the chip. The aluminum electrolyte capacitor acts as a damping element for the input filters and the cable. And it also, because it stands off a lot by several millimeters, will block part of the E field radiation. The bottom side, you see the two-stage filter arrangement with the two symmetric placed capacitors. So the AC currents in these filter capacitors will have opposite direction, and this way we will reduce the crosstalk into the other filter stages. Everything is strictly symmetrically here. Here's the 555 block to induce a frequency spread spectrum. And you also see a little 0603 capacitor, 10 nano, directly at the connection to my nice load resistor. Whenever you have a large load or a remotely connected load through a cable, you should add another LC high frequency filter to block the high frequency noise that is getting through the inductor. So 100 nano to 220 nanohenry with 2 or 6 or 3 capacitors is usually sufficient. Detailed look on the top side layout. You see the routing of the power ground, the symmetrically arrangement of the caps, the 2 loops. Here's an analog ground connection to the surrounding ground, to the output capacitor ground, and you see the surrounding cut. So this is a noisy ground that is separated. And again, this DC-DC converter ground, which is exposed to eddy currents from the high DIDT loops here and from the inductor magnetic field, is separated in a certain distance from the system ground. This is a DC-DC converter ground reference here. And actually, this is, I try to mark it in a different way. Let's see if it works. So this area here, where we have on the top side our hot loop components, should be free of any cuts. So we have a solid ground area under this input capacitor and the power stage of our converter, that the eddy currents can mirror image the high DIDT currents on the top side of the board. This via is V in and should actually be moved a little bit over here so that it's definitely outside of these loops. You also noticed that we have again a cut here, and this is because the eddy current density at these edges is not 0, and we want to keep it away from the outer area. So without the cut, we would still see at the side of the PCB where the connector is residuals of the eddy currents from the hot loop, and this we want to prevent with a cut. You also see that there's one ground connection, and this is actually the point where we route V in the layer underneath into this DC-DC converter block. And we have another ground connection where we have the output routed in the layer underneath to our load. So the cut out area here is larger than the one on the top side. The cuts do not align, so the top cut should be covered from this ground copper here. In a layer 2 or layer 3 in total, you see the V-in routing into the block. You see the output routing to the load. You also see that there's lots of ground copper with vias. And between all the routings we have here, we have copper, ground copper, to avoid crosstalk and provide a decent ground reference. We look at this DC-DC block as a 4-pole. We have current from the source and the return current in the adjacent layer directly at the same position. And the same to the load, and back from the load, the return current at one position in adjacent layer on top of each other. The bottom side of the ground of our PCB is solid ground in the whole center of the PCB. This is very important. And we have our filters and input connection moved a little bit at the side. And this is the result of all these efforts. You see the radiated emission test result, the so-called monopole test in the low frequency range. And usually if you use a fundamental fixed frequency of 470 kilohertz, you will have a problem to meet the average limit line of the CISPA 25. And you see here our first harmonic is 5 dB below the limit line. And this is due to the fact that we use a very small inductor, a very small switch node area, and we place the capacitors right next to the inductor and take part of the E field that is radiated here. It's also important that this inductor is very low profile. As soon as you use a higher inductor, like these examples here in the picture, that have 4.5 millimeter height, and unfortunately the inductor manufacturer places side terminals for the contact and the connection to the winding that are full height of the inductor. And if this is connected to the switch node, it's a strong antenna. And we have seen in our EMC test that this peak will move up by around 6 to 8 dB using this kind of inductor. So avoid anything that stands off the PCB to be connected to the switch node. Another solution is use E-field shielded inductors from Vishay, the IHLE series. They have an E-shield on top with a second or an additional terminal. This is also helping on this problem. Here we see the conducted emission test results, so low frequency with spread spectrum turned on now. Without spread spectrum, this would give one line that is around 10 dB higher. Same here. And this is the conducted emission average test result in the higher frequency range with 120 kilohertz resolution bandwidth. And you see we are well below the tough OEM limit of 12 dB microvolt. Here I have a picture for the same setup with a 3M part with 2 megahertz and spread spectrum. I compare two 6 by 6 millimeter coils, and one is 6 millimeter high and has an undefined start of winding. And you can see that this coil result is 6 dB higher over the whole frequency range, low frequency as also in the higher frequency range, than the 3 millimeter height one, which has a defined start of winding. So the inductor has a huge influence. And this is radiated emission with a biconical antenna, horizontal average result, and this is just above the noise level of the system. Very, very clean. We have a list of some frequently asked questions about the layout for EMC. The aluminum alcohol we covered already. There was also the question, is there any difference in the output filtering for a buck and a boost converter? So in a buck converter, we have a fully switched input current and a continuous output current after the inductor. The boost converter is a mirror image of a buck. It has a continuous input current through the inductor, but a fully switched output current. So all what we discussed on the input filtering of a buck converter applies to the output of a boost converter. How about a 4-switch buck boost? A 4-switch buck boost has a fully switched input or output current depending on the V in to V out ratio. So for a circuit that has wide V in, we have to apply filtering on both sides, input and output. We discussed already if the analog ground should be connected to the power ground at the IC level. No, the power ground is intentionally separated from the analog ground on the component side and only through vias and the inner layer to avoid crosstalk and noise from the power stage entering the system ground. When do you go for more than 4 layers? Whenever it's commercially possible, use 6 layers or more. You have to do less compromises, and you can provide at least 2 solid ground layers in layer 2 and layer 5, and you will see a much better EMC performance. Should you keep areas free of copper? Everything that is not needed for routing should be filled with ground copper, but every copper area has to have vias to ground in the corners to establish a solid connection. If this is not possible, and if you end up with isolated copper islands or so-called finger structure that have only a via in one side, you better remove them, otherwise you will create some patch antennas and strange effects. Only in this case you remove the copper. Does the input connector shape and elevation above the board has any influence on the EMI? So everything that stands off the board is a good antenna to radiate, but also to receive noise. So for example, if the inductor stands off like 10 millimeters and has a metal switch node connection with this height, it will be a strong radiating antenna. If you have a connector to the cable that stands off very high, it's a receiving antenna. So a flatter connector is better. The NC pins and the ground thermal pad of the IC should be connected to ground, as ground is the most solid and best plane in our board. The last question, number 9, the optimum number of spacing of wire holes to connect the top layer ground to the internal ground. There is no simple answer. It really depends. If we have a noisy ground area like the power ground, we only use a minimum required number of vias to block the high frequency noise of this ground area to enter the inner layers. If we have a quiet ground like the output ground that is also needed for heat sinking, we use, of course, a lot of wires, but there's no fixed number or rule of thumb. Okay, this is so far the presentation. I try now to answer the questions that came in during the session.
Thanks very much, Jens. So folks, this is your chance to submit any other questions that you might have for Jens. And again, please do so through the Q&A option that you'll see inside of the Zoom application. We'll wait just a minute or so and see if any questions come through. In the meantime, for those of you who maybe joined a little bit later, just a reminder that we will make the presentation available on MPS's website. That's monolithicpower.com/webinars. Again, monolithicpower.com/webinars. We'll go ahead and send out a link to that as well as information on future webinars. Okay, it looks like no questions today. So in this case, I'd like to say thank you again for joining us for our last automotive webinar of 2018. Oh, it looks like we actually have a question come through. Jens, will you take this one?
On the schematic, do you separate the input capacitor ground, output capacitor ground, and the system ground? Also, do you have any comments on the SV wire? I'm not sure what is meant with this. So on the schematic, we draw, so I can only recommend to you to draw the schematic already in the way how the components should be placed, which means that all the input capacitors should actually have already in the drawing the connection to the power ground. And you see here as an analog ground with a different symbol. You can do this, but under the line, yeah, it will help layouters. So analog ground and the feedback divider ground are usually they're close together. Yeah, you can see pin 15 and pin 13. So on the schematic, you can separate this already to indicate it to the layouter. This SW via, let's see, where is the via on SW? So again, we have whatever is in the schematic, we physically separate in the top side layout the power ground, the output ground, which is equal to the analog ground, and we separate it with the rest of the PCB ground to avoid high frequency currents from the high DIDT current loop. We can have here like 4 amp amplitude current flowing with a almost rectangular shape, disturbing the whole topside ground. We have made exactly of this PCB one version with this cut here and the layer underneath and without this cut. And we have seen a significant difference. So on switch node, we don't have a via. And you should not route the switch node in other layers. So this is the best approach. If you have to do it in a different layer, you should make sure that it is layer 3 and you have copper on top or bottom. Don't route it on bottom side of the board. Otherwise you pull high frequency noise here. Another thing that we learned is, for example, if you want to do a good thing and you think you add another capacitor parallel to these guys at the input and place it on the bottom side, you will make the performance worse. There's another question. Is there any way to create a low noise layout with inductor and output capacitance on the opposite side of the board from the controller and V-in cap? So the most important thing is that the input capacitors are right at the power stage. So if we have a monolithic synchronous buck, the input capacitors have to be directly at the chip. This is the most important thing. If you can try to use this symmetric arrangement, it gains a lot on EMC performance. The other big problem is the SW node and the inductor radiate E field. So you don't want to route this on the other side of the PCB, because then you have one side E field radiation and the magnetic fields from the inductor, which are not as terrible as the ones on the input capacitors, but then both sides of the PCB are disturbed. So you actually want the input caps, IC and the inductor, to be together on the same side. And if you can, put them under metal. So there is no real good way to do it. If you have to do it, you have to consider a shielding. I hope this answers your question, Jeff. There's another question. Sometime I have recommendation to remove a copper underneath a common mode choke or input filter components. Do you have any comments on this matter? Yeah, not really. So we don't use common mode chokes. Our goal is to avoid this. Our experience is a common mode choke or common mode EMI problem is a result of the E field radiation of the inductor that gives usually a common mode current. And so you have to block the E field radiation, and then you don't need this. And this E field radiation from the inductor you see especially in the monopole low frequency test, but you also see it in the high frequency conducted emission test. So in this example where we switch with 2 megahertz, this is E field radiation from the inductor. The guy that is 6 millimeter high has much higher E field radiation. If you would use a impedance in the ground or a common mode choke, this would go down. But I have no strict opinion on placing copper under the common mode choke. It's probably a little bit better not to place copper there. I hope this is answered. Any more questions? There's a question again from Jeff. Do MPS modules consider EMI, or if we are concerned with low EMI, should we stick with discrete implementations? Yeah, the modules have some advantage because the distance of the placement of the components is not according PCB rules, which have quite a bit distance. Inside the modules, we can use the distance rules from IC technology, though actually the components are much closer together, the loops are smaller, so they have a little EMC advantage. We have special super low EMI shielded modules for people who are really concerned, with a metal can on top. Hope this answers it. Any more questions?
Looks like that's it. So, oh, one more.
So dual input filters seem to have less PCB space than a single filter. What about the price? Yeah, this is pretty simple. If we compare these guys, these components are very cheap and very small. And this 10 micro is quite a little bit bigger. So if you look purely at the core material, if you have like what I used, the 3 amp goal, you have a 0805 and you have a 2 by 2.5 millimeter coil, and this is a 10 by 10 by 6 coil, or a 5 by 5 by 5 coil. So this is much more core material and it's much more expensive than these things. I hope this answers your question, Ling.
Okay, good question, Ling. Thank you. So folks, thanks again for joining us for our second Automotive EMI webinar and our third in our ongoing automotive webinar series. And special thanks to Jens Hedrick for speaking today and providing us all with some great knowledge on layout techniques for EMC. So stay tuned. We will send out an email with a link to revisit today's presentation, to access the material in PDF form, as well as future invitations to upcoming webinars. Thanks very much and happy holidays.
Thank you for your time.